So this is where I had you to end up, and I told you to answer A and answer C, and then come back and we'll double check our answers because, folks, we might be skipping ahead a little bit, but that's all right because this is really relevant to what we've just discussed. So for part A, they told you to take an alcohol, and that alcohol looks like this, and we're going to add HBr and a little bit of heat to this in order to get a product. So they want to know what kind of thing is going to form. All right, so let's talk about the mechanics. Let's talk about the mechanism here. OH is going to get ugly. That hydrogen from the acid, bam, is going to hit OH in the eye socket, and it's going to give it a black eye, and it makes it ugly, and carbon's going to make it leave. Well, this OH group is on a carbon, and this carbon's attached to two others. So this is a secondary alcohol. Secondary alcohols undergo SN1. Meaning rearrangement can happen if it wants. And SN1 means that it doesn't have to cheat. So what that means to us stereochemistry-wise. Here's my molecule. I'm going to draw two versions. You'll see why in just a second. So the OH group is going to leave because it's been protonated, away it goes. It's not going to rearrange. If it goes left-handed, it's secondary. If it goes right-handed, it's primary, so it's perfectly okay with where it's at. And bromine will go on in its place. Simple as that. There's our first one. This also means that Walden inversion did not take place, right? I started off with a dashed wedge. I end up with a dashed wedge. That's okay with SN1. With SN1, you do not have to sneak through the back door. It's not a requirement. You can if you want, and that's where our second choice is going to come in. So this OH group could get protonated. It could leave. That forms a carbocation. It doesn't shift, just like before. However, when the bromine comes in to go to this spot, it could sneak through the back door if that's what carbon wants. And if it sneaks through the back door, it flips the stereochemistry. What was a dashed wedge is now a solid wedge. So, folks, we get both of these. We get version 1 and we get version 2. Both of these, they look very similar, don't they? They have the same number of carbons, same number of hydrogens, same number of bromines. The difference is the orientation. The left-handed and the right-handed version. Let's do a quick review of what R and S actually is. All right, so with R and S, I'm not going to do it here exactly because they're not really after us labeling something as R or S, but typically what you have in this field is a carbon, and this carbon is what we call a chiral carbon. And a chiral carbon means 4 different groups, 4 different things attached to it. So we often do one that goes straight up, and we often do one that goes straight to the right-hand side or left. And then the other 2 bonds, one will be solid and one will be dashed. So in the world of stereochemistry, we normally like to put our high priority groups on the dashed wedge whenever we can. And this, or lower. So that lower priority group will be almost every single time a hydrogen. Something with a lower group number. That's how this worked. Hydrogen is atomic number 1. Nothing is nastier than hydrogen, so we put it in the back every single time when it happens. Well, maybe we have, I don't know, a bromine, maybe an OH group, maybe a CH3 group. I just randomized it here. And we want to use stereochemistry rules to label something as R or S. So here's a quick review. If you did not talk about this in Chem 251, what a shame. You need to let me know who that instructor was so I can write a nasty gram to them. So I look at bromine, I look at oxygen, I look at carbon, I figure out the highest atomic number. The highest atomic number here is going to be bromine, so this is going to be rank number 1. And then oxygen and carbon comes next, so oxygen is going to be ranked 2, and then that carbon is going to be ranked 3. All right, so here we go. 1, 2, 3. And if you look at the way that this is going, it's clockwise, right? This clockwise rotation means an R stereochemistry. If I wanted to do an S, very easy from this point. The only thing that I have to do in order to flip R to S is just switch two of the groups. So, for instance, what that would mean, let's switch the BR and the OH together. All right? So the way that I would do that, OH goes up here, BR goes right there, and then let's just keep the others the same. It's a very easy way to switch back and forth. So now bromine is here, still group 1. Oxygen, still group 2. That methyl group, still group 3. And now we have a different rotation. This is counterclockwise. And that counterclockwise is S, which stands for sinister, because left-handed people like me are from the devil. They're sinister. They're evil. At least that's what they thought back in the day. All right, so here's R and here is S. And that's just a quick recap of stereochemistry that was back in the day. All right, now let's take a look at C. For part C, they give me a bigger, nastier molecule, don't they? It looks like this, and then here we have 2 prongs, 2 little feet. Oh, look, it looks like a little bird. And here's OH. And we're going to add HCl with a little bit of heat. And they want to know what would form. Stereochemistry-wise, what will form? All right, well, this OH group in the problem, that's on a dashed wedge. Once again, let's think about mechanics. Let's think about what types of products are going to form, so forth. I'm going to rewrite the reagent. There we go. And I'm going to look at the HCl and say, okay, the purpose of the HCl is to protonate the alcohol group. Bam! Give it a black eye. This OH group goes away and leaves. And what we do is we form a full-blown carbocation here. How do I know that? That OH group is on a carbon, and this carbon is a secondary carbon. So, because of that, SN1 will go forward, which means carbon frees up a carbocation, gets its life together, and then brings in the incoming group. It also means that things do not have to flip Walden inversion-wise. Sometimes they can come through the back door, sometimes they go through the front. All right, so if I take a look at this molecule the way that it is right now, that carbocation at this point, let me draw this a little bit better. Let me get rid of that bond. That bond's not there anymore. Nothing's attached there except for a carbocation. That carbocation looks like it goes left-handed. The reason is because at this point, this is a tertiary carbon. A shift will happen, folks. And a shift happens because if this carbocation can move here, well, this carbon, what does it have to switch? There's no hydrogens there, so it's going to switch a methyl group. And now that carbocation ends up being in a tertiary spot. And that was due to a 1,2 methyl shift. There was no hydrogens to switch. It had to be a methyl group. So now at this point, the chlorine is going to come in, and it's going to attach to that spot. And that chlorine is going to go there. The same thing is going to happen on the other round. I'm going to see the chlorine go into the same spot. Now let's think about stereochemistry, because that's what the question wanted. What stereoisomers do the following reactions form? All right, so if I go to this OH group was a dashed bond. And when this SN1 reaction happens, it can go through the front door and stay the same stereochemistry. So it can still be a dash bond. But because it's SN1, it can also go through the back door and it can Walden invert. So Walden inversion can take place, and we also get a solid wedge that can happen as well. In one version, the dashed wedge, that chlorine is pointed away from you. And in the other version, that chlorine is pointed towards you. That is the difference between those two molecules. Same number of carbons, same number of hydrogens, same number of chlorines, same molecular weight. Stereochemistry-wise, they're different. The orientation is different. And that is what stereochemistry is all about. So that goes back to a general rule of SN2 and SN1. SN2, Walden inversion has to happen. You will get a flip, and it will be 100%. That's the only way that those can go forward. With SN1, it doesn't have to be a flip. You're actually going to get both. Both choices are going to exist. Okay, so that's where this video is going to stop. I'm not going to talk about B and D. The reason is because we've not talked about those reactions yet, and I want to do something a little bit more before I go into those reactions and tell you a little bit about the mechanisms. What I can say before this video stops, though, is that we're often talking about tertiaries and secondaries and primaries and chlorines and bromines. Just maybe a quick general summary of everything that we've talked about so far. First off, chlorine out of the halogens will react the slowest. It still reacts. It still gives us a reaction. There's not a doubt in that at all. But out of the chlorine and the bromine and the iodine, it is one of the slowest out of the halogens because it's a little bit prettier than the bromine and the iodine brothers and sisters that it has. Because of this, it's not uncommon for us to throw in zinc chloride, and this is going to be a little bit of a catalyst. So anytime, once again, you see the zinc chloride, that's why we're doing that. It speeds the reaction up a little bit more. Tertiaries, as far as carbons go, tertiary alcohols, secondary alcohols, primary alcohols, tertiaries react the fastest because they leave behind a very stable carbocation, and that's very good for the reaction. The molecule feels good that it can handle that positive charge because it's on a tertiary carbon, and then primaries are going to be the slowest. So with the primaries here, the primaries are the slowest, and if you react that with chlorine, which is also the slowest, then you really do have to add zinc chloride into that solution to get that to go forward. So that's just a little caveat. You know, it's not a trick question, but this is why you're seeing that zinc chloride involved sometimes, and sometimes you're not. It just really depends on the type of alcohol that they're adding with it. That also can lead me into a qualitative test called the Lucas test. The Lucas test is really going to be for alcohols here. And what happens is that I can have tertiary and secondary and primary alcohols, and I can add in zinc chloride and a little bit of heat with some acid, HCl. When I do this, the tertiaries are very stable. It doesn't need a lot of persuasion in order to react. So if I have a tertiary alcohol and I involve it in the Lucas test, number 3 tertiaries will give me immediate reactions. And that means cloudy. They turn very cloudy very quick. The reason is because if you've noticed with these byproducts, we often generate water from the alcohol group, and then we have an alkyl bromide or an alkyl chloride that gets formed as well. And these alkyl bromides or chlorides, these are really organics. And those organics do not mix with water. So we see a cloudy solution that begins to get formed. That's why that happens. So tertiary alcohols react very fast. They happen immediately. You will see a cloudy solution almost as soon as you put these two things together in the same test tube or the same flask. The reason that they're turning cloudy, because you're generating an organic alkyl halide mixed with some water, and they are immiscible. They do not mix very well. Secondaries take a little bit longer. It takes about 5 minutes for them to go cloudy, and they go cloudy for the same reason. But if it doesn't turn immediately, this is a confirmation to us that I do not have a tertiary alcohol in my hand in that test tube or in that container. If it does turn cloudy within 5 minutes, maybe a little bit longer, not too much though, 5 minutes, give or take a little bit, then this is a very good sign that I have a secondary alcohol in my test tube or in my container. And primaries very often will stay clear, believe it or not. They're just so stubborn that I don't see a generation of a lot of alkyl halide. Now, it could be making alkyl halide. It's just not in a large amount. And because of that, I don't visually see that, because that immiscibility between it and water is not as obvious as the secondary and the tertiary. So this is all about kinetics. It's all about speeds of reaction, and this is what we call a Lucas test. It's one of the, I would say, more common qualitative tests that they do in the organic arena. So primary, secondary, tertiary alcohols can be determined by what we call the Lucas test, and that's how it works, and that's why it works. Now, the problem is that we are also assuming very small molecular weights here. I can't choose big, huge alcohols for this reaction to go forward, right? So I've got to limit this in a way. Very small molecular weights, which is a small number of carbons. Otherwise, everything is going to look cloudy and it's not going to make any sense. I need some miscibility, at least a little bit, okay? So limit the alcohols to less than 6. That's typically the rule of thumb with the Lucas test. All right, so that's where I'm going to stop this video. A little bit of qualitative analysis here. If you have to take that course a little bit later on, depending on where you go, these are the types of things that you can look for. So just to wet your whistle a little bit with qualitative analysis. So the next video, we'll move on and we'll talk about other alcohol reactions that can take place.